Good afternoon. Today we're going to dive right into some of the current industrial control system security solutions that are available. So what is the problem currently? There's a lack of resources for jump-starting the ICS security process. And what do I mean by that? So imagine you're an industrial control systems engineer and you have no experience with security. You've inherited a process that has run perfectly for 10 years, and your security engineer suddenly comes to you and says, due to recent events, we really want to put some more security controls in this process. So you are now responsible for going out to find these security tools. Now, without the experience in security, that might be difficult for an ICS engineer. And the opposite is also true. A security engineer with no experience in ICS is also going to have the same difficulty. And this is often because the vendors are promising to address these solutions, but the lingo can be difficult to understand if you don't have insight from both sides of the fence. Additionally, when you go out to look for these tools, there's an enormous amount of noise currently. You have new companies starting, releasing new products, old companies buying the new companies, re-releasing the same product with a different name, and it's very difficult to maintain a good view of the current security landscape for industrial control. So what is the solution to this? Well, the perfect solution is that we have a complete list of every tool available with a tested and completely unbiased description of what the capabilities of these tools are. You basically group each tool into a subset, and then you test each subset with a standardized test. This way you're comparing apples to apples, and you're not trying to get different solutions to the same problem. So at the end of the day, you would get something right like an Underwriter's Laboratory-esque sticker for this tool can do these things. And this is a bare minimum. This helps your consumer determine, not what the best tool is, but at least you have a guarantee of what it can do. So what I'm presenting today is kind of a small step in that direction. It is a basic framework for comparing ICS security tools moving forward, and a survey of roughly 60 tools that are currently available and the different categories that they go into. So there's been some related work on this recently. Dale posted a blog post in May of last year while we were doing this research, talking about how busy the anomaly detection market is for industrial control systems. So it's good to know that somebody else was kind of on the same track in terms of what they found. In addition to this, the University of Illinois Information Trust Institute and this other awesome industrial control system security are great resources in terms of open source tools, as well as ICS network auditing tools and other various educational references. We're not going to go into SCADA 101, but this is where you'd go if you needed that. But one of the issues with these references is that they don't really go into commercial tooling. They go into university-backed research or open source tools, but they don't talk about what most businesses are going to deploy commercially. And then finally, we have NIST 882, the guidelines for industrial control system security. This is more of a reference for the framework that we designed. Overall, this documentation is a little heavy-handed for what we decided we wanted, and gave us too much granularity, so we reduced it to a significant subset. So the scope of this work is that we're looking at security solutions that are currently available for the ICS environment, with two main caveats. One of them being that we only focused on security-related tooling. We didn't include any vendor-specific tools unless they were specifically security tools. And now these tools would be useful for something like a CERT team if you're trying to get this information, but you don't really want to use them in an enterprise deployment. Additionally, we found tools that we considered enablers. Now, these enablers are not necessarily security tools in of themselves, but we believe there's something that could be useful for building these security tools, and they're typically hardware tools. So these are things like JTAG readers and scanners. And the second major caveat is that no attempt was made to verify the claims by the vendors of these tools. And what do I mean by that? I mean, we took their description on their website and categorized based on that. There was a few problems for why we didn't get to buy all these tools and test them. One of them being It was outside the scope of our funding, and you have a couple problems with the enormous scale of trying to get a representative sample of not only the ICS equipment, but also the ICS networks. You can't test a single tool on a single representative network and say that it's going to perform the same everywhere. An example is the ICS challenge going on here, midstream oil and gas, can be completely different than electrical generation. So just a quick overview of what our summary looks like. We have 4 main purpose zones, and in each zone we have 6 different purposes. I'll go into this in more detail later on in this presentation, but we're going to go into definitions of each of these zones. So moving on to the notional ICS architecture, this is going to be more interesting to people that want to adopt this research, continue it, make it better. Later on, I will talk about more of our just straight findings. So the 4 zones that we decided on were enterprise, control center processing LAN, local HMI LANs, and your controller field I/O devices. So most ICS engineers are probably more used to seeing an architecture that looks something like this. DMZs broken out, operational networks by themselves. What we decided was we didn't need this type of granularity. By reducing the granularity, we were able to much more precisely put tools where they needed to be. And in that case, it was easier to, we didn't want to get caught up in too many different zones and purposes. So I'm going to go into a couple definitions. Like I said, this is the formal definition that we decided on to categorize these tools. So your enterprise definition is going to be your information technology network. This is used for billing and business purposes. You're going to see your domain controllers, web servers, enterprise desktops, and really what's important is it wasn't a focus. We didn't include any tools that were enterprise only, and really we only provided this for perspective of tooling. If a tool expects to be deployed in an enterprise environment, but wants access to your SCADA network, and your security architecture says that you air-gapped your SCADA network, that could be a problem for deployment. Next, we move on to the control center LAN. This is a local segregated network used to support SCADA, billing, log gathering, et cetera. This is where you're going to see your OPC servers, historians. It's important to know that this is mostly a Windows environment. A lot of normal IT solutions are going to work here because you don't see a whole lot of ICS protocols yet. You see some going to your OPC server, your historians, but really your IT solutions are going to work more or less. As we go down another layer into the local HMI LAN, this is a different story. So these are your computers and kiosks at remote substations or buildings that provide on-site feedback and local troubleshooting. So this is where your ICS protocols start to become prevalent, and while Windows is still the back end for most of these HMIs, your IT security solutions tend to fade, and that is mostly due to the fact that an IT solution, when it finds data that it can't parse, is really just going to make it a binary blob and continue on its way. And that's not what we want. And finally, we have the controller LAN. These are your embedded field devices that are exposed to the elements in remote sites, used for switching and raw data gathering, your PLCs, sensors, actuators. This is primarily a bare metal environment or proprietary environments, which makes it very difficult to generalize a solution. So by what I mean by that is, something that might work for a Siemens controller isn't going to work for an Allen Bradley controller. Additionally, deploying on these networks is very difficult, often because there are serial protocols, proprietary ICS protocols, or standardized protocols that a vendor has decided they're going to extend but not document. So now we move into the 6 different tool purposes that we decided on. We decided on 6 because this way we could categorize each tool accurately without adding too much complexity to the process of categorizing these tools. So the definitions we came to were indicator of compromise detection, network traffic anomaly detection, outlier analysis, log review, system artifact review, and reverse engineering analysis. So you're going to see some tools as examples in these slides. This is by no means an official backing. I tried to pick tools that were generalized and a lot of people would have awareness of, so that it has a great example of the general purpose of these tools. So an indicator of compromise is a forensic artifact observed on the network or host that with high confidence indicates a computer intrusion. Examples of these are hashes of known malware, signatures of malicious network traffic, or URLs or domains that are known to distribute malware. So a successful tool will be able to detect all malicious data that is directly bounded by the provided rule set. An example of this is Yara. If you give Yara rules, it will find every file that follows those rules. It will not mutate those rules. It won't look for anything other than those rules, and is directly bounded by what you provided. Moving on to network traffic anomaly detection, this is based upon the statistical properties of the network that you deploy it on. So some of these properties can include IP addresses, ports, frequency of communication, net flow data, and anomaly detection is different than indicator of compromise detection by not requiring distinct manual updates to find new threats. So a new threat by definition is an anomaly on the network. Now this line blurs a little bit in ICS because new threats typically utilize normal operation, but you can start looking at things like temporal references to the differences of what is an anomaly. So a successful tool should be able to be trained on a network of normal traffic and then be deployed with the associated model to determine anomalous traffic. An example of this is Bro IDS with utilizing the Bro scripting module as well as Snort. Now we're going to move on to outlier analysis. It's the ability to analyze anomalous data for future threat intelligence. This data is usually identified by searching for anomalies across hosts that share common configurations. A successful tool will be able to scale to large data sets and will help an analyst find meaningful differences. So examples of this in the enterprise environment is OS Query, where you install this on multiple hosts and you can query things like running processes, users that are logged in, permissions these users have, and other things. And then you can use these to implement or to import into Splunk and then run additional analytics on. So a point of contention is, what's the difference between anomaly detection and outlier analysis? Now, I used to give the definition of the technical differences that we decided on, but just to make sure that everybody's still awake, I've decided on a new analogy. So an anomaly is like Neo from The Matrix. He is outside of the realm of what you would expect, but still very much in it. People are surprised when they see him, but it's not unheard of. And an outlier is more like Chuck Norris. There really just is no definition. Now, if you don't like the analogy and you'd like to discuss the technical differences, come find me afterwards. But right now, we're going to move on. So moving on to log review, this is the process of analyzing computer-generated records that typically include a temporal reference. Difficulties in log analysis include the removal of uninteresting data while also keeping the integrity of your log file. If you remove too much, you've lost the usefulness of actually logging. So a successful tool may implement anomaly detection in the logs to quickly generate areas of interest for an analyst to look at, or may be able to ingest multiple versions of logs in order to generate a timeline of events. Some examples of this are Splunk and the Elk stack. The system artifact review is the process of analyzing system artifacts that are created as a byproduct of execution. It's important to realize that these are short-lived artifacts, and if this is not something that you have caught due to anomaly detection or indicators of compromise, they're most likely going to be gone. These are tools that you kind of use post-boom. And some examples of the artifacts that you're going to be collecting are registry files, data files, memory resident information, and a successful tool is going to be able to extract all possible relevant information and store it for later analysis. A great example of this is volatility. This is great for desktop environments, but obviously is not exactly ported to an ICS environment. And finally, we have reverse engineering analysis. Reverse engineering is the process of extracting information given some set of data. This data often refers to files or firmware from a device, but can be extended to network traffic as well. So a successful tool is going to be able to disassemble multiple architectures or protocols, as well as display the information that aids the analyst in reducing the amount of time spent reverse engineering. Some great examples of binary reverse engineering tools are IDAPRO and Binary Ninja, and when you move into the protocol reverse engineering, you have Wireshark and NetZob. So now we're going to talk about the survey results. This is where it's more interesting if you just want to apply the data that we found and you're less interested in expanding or adopting the research. So reading the results, this is just a snippet of the results from the real paper. You have 4 major columns. Each column is a zone that we have talked about. In each zone has 6 purposes that the tools fulfill. Obviously, a filled-in block means that that tool fulfills that purpose. The orange numbers indicate how many tools fulfill that purpose in that zone. And then we have these 2 other columns, target and acquisition. So the target is going to be how the tool consumes data. And then the acquisition is going to be, is it a commercial tool? Is it open source? Is it university backed, et cetera. So here are some of the resulting insights that we gained. Each purpose is in order from IOC detection to RE analysis, and each bar on the graph is in zone order from control center, local HMI, to field IO devices. So one thing that's important to note is we eliminated enterprise at this point because that's not something we're really interested in. And so analyzing the rest of the data, we did confirm that there are a huge number of network traffic anomaly detection systems currently available. Now, this is likely due to the fact that they're fairly easy to adapt from an IT solution to an OT solution. As soon as you add additional protocol parsers and you implement the standards of that protocol, you now have an ICS security solution. And we also noticed that field IO solutions are very difficult to find, likely due to the fact that it's very difficult to deploy directly on a field IO network. Most tools try to get at least one layer up to the point where it's wrapped in IP at least one time and analyze it at that point. So there are pros and cons to this. One of the issues could be that you're missing data that doesn't actually get up one layer. So we went on and did gap analysis for 2 zones, the control center and the field IO devices. The reason we chose to only do 2 zones was because the local HMI LAN really doesn't have any of its own unique problems. It really kind of inherits from both the control center and the local or the field IO devices. So in the control center zone, in the indicators of compromise, we need a better understanding of bump in the wire devices or black boxes on the network. So you need to be able to tell when your Ethernet to serial converter is having a firmware update. You need to be able to tell when your VPN black box is reconfigured. And these are things that you might be constrained on your configuration because the vendor doesn't necessarily give you administrative privileges to everything in the box. Network traffic anomaly detection, we really need expansion into ICS protocols. There are a lot of simple ICS protocols or more common ICS protocols that are implemented already. Modbus has a very significant following, as well as DMP3 has a operationally acceptable following, especially in open source tools such as Bro. And outlier analysis, most embedded devices on the network don't provide direct access to the data. So you can't have a configuration management system without access to the configuration. In log review, in a Windows environment, most log review is fairly well documented. Everything is capable of logging remotely through syslog, and analyzing these logs is very easy and well thought out. And system artifact review, we have solutions such as endpoint protection as well as vulnerability scanners that go through and find different artifacts on the system. These are really well supported for Windows. Linux, we have less support, but overall it's relatively strong still. And reverse engineering analysis, this is well covered by multiple tools that are readily available. You have static and dynamic analysis, and a lot of the automation is in place to get a binary or protocol into a format that you can start the reversing process very quickly. Moving on to the field I/O devices, it's a completely different story. The indicators of compromise detection, there are a lot of new tools, and none of them have been tested. Many tools suggest a wide range of support, but without testing, it's really difficult to determine if these are accurate or if they have a different definition of what this means. Network traffic anomaly detection, common ICS protocols such as Modbus are very well supported. DMP3, as I said, has operational support. There are many objects that it doesn't support in most cases. They're typically lesser used objects on an operational network, but it is something you have to implement or else you don't know what you don't know. Moving on to outlier analysis, log review, and system artifact review, there's almost nothing to talk about. There's a huge lack of tested tools. Tools that claim to do one claim to do all of them. And meanwhile, logs and system artifacts are near impossible to retrieve from these endpoint devices. The vendors don't expose a method for us to get the logs out in any other way other than their tools. When you move into reverse engineering analysis, the tools are flexible enough that they can disassemble multiple architectures or protocols, but you lose a lot of your automated analysis. So while we were doing this research, we found a lot of additional research opportunities, and these were things that were going to be the most bang for your buck in terms of the amount of effort you put into it versus the amount of help it does for the community. So extending tools such as open source Bro is a great choice. So right now, it doesn't have extensive support for field protocols. Additional protocol analyzers would expand its use dramatically. And while you still don't get a support contract with an open source tool, it's much more viable to deploy as a commercial tool. So as I said before, Modbus is fairly well supported, DMP3, but once you get into more exotic protocols like 61850 and all the protocols that it entails, support is not existent, and they don't even have protocol analyzers. So moving on to log extraction tools for field I/O devices. Currently, vendor tools are your best option. This is typically because in the actual PLC, these logs are reduced into a single byte, and that way it doesn't take up space on your device, and then your vendor tool pulls those bytes out, expands them to a specific log entry, and then shows them to you. So creating tools that would be able to aggregate log data from multiple different vendors in a way that's easy to use would significantly increase the visibility into these devices and some of the problems they have. And system artifact review, there are very few ways to retrieve any artifacts from these devices. Not many vendors implement some view into live memory or running processes, and those that do typically are used for support contract usage. So these are binary blobs that you download from the device. They don't tell you what it is, how it's formatted. They just say, send it to us and we will use it to troubleshoot. So finally, how to improve this resource specifically. One of the major things is to keep this up to date. We're going through another revision currently that's looking at roughly 15 more tools in each total. And as soon as a resource like this goes out of date, it is totally useless to the community. So the next thing we'd like to add is cost. Obviously, everyone would have to go to a vendor and acquire a quote to make sure that the cost is accurate. But if you can give a ballpark estimate, then this is very useful for commercially trying to decide what tools you want to deploy in your network. And finally, one of the largest things that would be the most useful for this resource would be experimental comparison data. Now, this would be a standardized comparison, a battery of tests in each zone and each purpose so that you're comparing the same functionality between tools. Additionally, you would want to say what type of ICS device was covered and the protocols that were supported for these devices. So finally, I'd like to give a special thanks to Michael McCarty, who was a co-researcher at INL, didn't get to make it out to S4, and Rob Lee at Dragos, who gave us a lot of insight and various tools that not only included his own tools, but also additional tools to look at. So if you're looking for the actual research that will have all of the data included in this, there's a link to my LinkedIn, or you can go to osti.gov and look at the document number 1376870. Thank you.